Professor Garello, for the introduction and the welcome here in Politecnico di Torino. It's always a pleasure to be here and visiting you. In this opportunity, together with Jorge Finoquieto from the Universidad Nacional de Córdoba, we have prepared, hour and a half, more or less, seminar on routing on the space internet. And the idea is to touch on different aspects, on the different domains that where routing can play an important role in the space internet, and also dive a little bit into protocol design and protocol considerations that must be taken in order to have these space networks actually deployed and operating in space. Just to give you some general motivation here, let me just minimize this a bit so it doesn't bother anyone. So we are talking about space, right? So we are, just in case you have different backgrounds, we are motivating also that nowadays space industry is actually quite strong and it's moving forward, mostly as you have seen on the news and so on, by SpaceX and Starlink, and there is very big companies, but also quite strongly on the European level with very big companies, and also there's the European Space Agency putting forward a different set of projects, which you can see in the last, let's say, 20 to 30 years, the trend is increasingly growing. And we have seen many missions and examples that are actually arguing for an increased presence in space for observation purposes, for communications. Communications is by far the largest application domain nowadays, but also observation of the planet, meteorology, and also navigation, exploration, and also other military uses. So space is, I would say, at least on my life, is stronger than ever. This is definitely a growing trend on interest on the industrial side, but also on the academic side. Since ever, basically try to strand, master, and profit from space. And with this in mind, networking is kind of the fundamental aspect if we ever want to support either crew missions with humans on board or robotic missions for exploration. Networking is a must. And basically, we understand networking as the way of communicating between multiple assets in a cooperative manner. And this is the object of study that which I care about, and we want to explore a little bit with you today. So what we have to propose? So we are proposing a seminar divided in two different parts. So the first part is going to be me talking to you, where we're going to be looking into three space networking domains. I want to split the object of study into three parts, which are mega constellations, namely these are very large scale constellations, satellite IoT, and also quite an emerging trend now these days, and the solar system internet, growing in, if you can see here, actually, we can kind of create a quick taxonomy of what actually divides these three domains. So with mega constellation, we're talking about resourceful systems, which are very close to Earth, which actually means that we are talking about very low latency and low propagation latency in particular. When we move to satellite IoT, we still have constellations or networks around the Earth, but which are resource scarce, because these are either smart satellites or these are IoT devices which are potentially battery powered. And when we move to a more ambitious concept, which is the solar system internet, we are now moving far away from Earth. And we are also resource scarce because sending something to other planets is super expensive. So with this taxonomy in mind, we are going to explore different, let's say, challenging research topics that are directly related to routing, with a particular focus on computer science, which is more a little bit more profile, applied computer science. In the second part, Jorge will present us a bit more of protocol engineering. So how do we design the communication protocols in this type of space networks with a specific focus on paradigm, which is kind of the enabling paradigm in deep space networks, which is store, carry, and forward data handling, where data can be kept stored in a given for a given period of time in intermediate nodes. And this basically challenges a bit the assumptions that we have for Internet protocol nowadays. And Jorge will dive into these terrestrial Internet assumptions that are basically broken by this store, carry, and forward approach. The delayed channel networking architecture, we try to capture all these effects, and the bundle protocol, which is the materialization of that architecture. And finally, Jorge will also dive into security aspects about these protocols, which are also quite challenging when you don't have immediate communications with your end node. And the mood during the talk is going to be, I mean, we are very limited in time, and we have a lot of topics. So we're going to possibly touch them a bit superficially. We're going to share pointers if you are interested in some of the topics. And you can either take a dedicated read afterwards, or you can basically interrupt us, and we're happy to go deeper if you need, either during the talk or afterwards. So I'm happy if we keep this informal, and you can interrupt us and pose questions as you need. Good. Yeah, so typically, I mean, just in case someone is not from the space context, I'd like to give a very quick overview of what type of orbits we typically have in mind. So when we talk about constellations or near Earth services, we're typically talking about LEO or low Earth orbit systems. And these low Earth orbits are basically orbiting in altitudes which are in the order of 500, 600, up to 1,000 kilometers altitude from the surface of the planet. And the orbital dynamics impose that these satellites will move in the order of around 7 kilometers per second. So this means that in practice, you will see a satellite emerging in the horizon and potentially hiding in the other side in the order of 10 minutes or even less, depending on the elevation of the pass. But for years, we have also been looking at geo orbits. These are an orbit which is far higher than 1,000 kilometers. We're talking about 35,000 kilometers, which orbits at precisely the rotation speed of the Earth, which means that in practice, the satellite from the surface is seen as a fixed point on the sky. For years, this has been super practical because for communication system, you don't need to have a tracking antenna or anything. Just point the antenna to the geo position, and then you have a stable communication links, although with a very high distance range. And then also we're going to be covering a bit about deep space today, where we're talking about distance to the moon, which are in the order of 400,000 kilometers distance, or even Mars, which basically has the 3 orders of magnitude larger than that. And with the issue that happens on deep space is that you can imagine the link budget is definitely challenging to meet. Plus, also the latency that we have in these links is already starting to be limited by the propagation latency, even at the speed of light. At this distance, we're talking about 1 second of propagation time, and here we can be talking about 10 minutes or more of propagation time to remote planets. And you can start thinking, if you make a quick reasoning about how do we think on internet protocols working in such a context, then you can imagine an ACK coming back to you after 10 minutes one way, 10 minutes the other way. So 20 minutes, you get an ACK of a packet you sent. So you can easily imagine that protocols that we already know in our current day-to-day internet get broken very easily. These are topics that are going to be covered mostly by Jorge afterwards. So let's start with the first domain that I mentioned. I want to split this in 3 domains. And I think the one that captures our attention the most on these days is Starlink or mega constellations. And of course, Starlink is possibly the main, let's say, example of mega constellations. And this is an actual animation by Mark Handley. I definitely, if you ever want to get intuition on how this system looks like, I mean, this guy has amazing visualizations. And these are the 3 shells of Starlink. Basically, these are 3 low Earth orbit shells operating all together. And yeah, so what can I say about Starlink? So Starlink is nowadays has the 63% of share of the full satellite fleets that we have operating in orbit nowadays. So it's by far a major actor in the space communication industry nowadays, with a clearly growing trend of keeping this dominance by far and increasing this presence. And it's basically closely followed by other actors like OneWeb, which only has 628 satellites. I mean, and we basically 1 order of magnitude away from Starlink. And we basically, by the middle of the table, we start to see some applications which has to do with observation. So the very first, or by far the largest satellite share that we have on the orbit at the moment are for communication purposes, in particular, broadband communications, internet type of communication services. And then we start to see some observation missions like Planet Labs. These are companies that also host constellations, which are smaller in satellite counts, but they provide observations, so imaging data from the space. And as you can see also on this quick table here, space constellations are also becoming a geopolitical asset besides their economical purposes. And the military participation and involvement, you can see also here on this table, is actually becoming stronger, not only like mentioning Chinese or Russian government explicitly, but also the participation of the United States in standardization of networking technology for military use. So this is quite a particular context, I believe, that we're having nowadays in space that has, of course, its advantages and disadvantages. It definitely is pushing forward the industry quite a lot, but also opening quite a lot of concerns about what's the role in space in the current geopolitical moment. Going a bit more technical now, so how these mega constellations work. So we have satellites, which are typically equipped with at least 4 intersatellite link terminals. These are, in this case of Starlink, these are optical intersatellite link terminals. They don't use radio frequency, but they use laser beams on the satellite to communicate data with the neighboring satellites. And because of the orbital dynamics, we typically have one intersatellite link antenna that talks to the satellite, which is on the same orbital plane in front of us. Another optical terminal will talk to the satellite that is on the same orbital plane that behind us. And because of the orbital dynamics, these satellites can fly kind of in a train, one after the other, and therefore these terminals can be fixed or with relatively limited need of pointing needs. And then we typically have 2 crosslinks with the cross planes of the orbit that helps you to communicate across orbital planes. And because of the orbital dynamics, in the case of this particular Walker Delta constellation shape, they basically move in angle with respect to the central satellite. But in the end, what the effect that you get as a result is that you have kind of a mesh topology that is built thanks to these 4 the satellite links terminal. This movement that you see here with the crosslinks is typically achieved by means of gimbals. These are typically small motors, small engines that helps you turn and point your terminals to the satellite, and basically every orbit, which in case of LEO at the speed I mentioned is in the order of 19 minutes, you basically repeat more or less the tracking pattern, and in such a way you can construct such a topology in that way. Once we have the topology built, the question arises immediately. So what do we do with routing? So which is the logic that will guide the decision on if I receive data on one of these 4 terminals, which is the logic that will enable me to respond, which is of the 3 terminals, or my downlink link is actually the resulting transponder I want to use to offload that data. And that is, in essence, a routing question by networking definition. And when we talk about routing, those that comes from engineering or computer science, we immediately know that Dijkstra is one of very popular algorithm to find the shortest path in a graph. And as I said before, we can now, based on this orbital configuration, we can build a connected graph of all these intersatellite link terminals. And definitely we can run Dijkstra on this graph on the expectation of achieving a shortest path, considering a given metric. One potential metric would be the distance. We want to achieve the lowest distance to a given destination or the lowest number of hops. You can use different optimization criteria, but in general, Dijkstra seems to be a potential solution. And Dijkstra, as you might know, is an optimal algorithm, so we are not going to beat Dijkstra in terms of optimality, but there are some tricks that we can leverage from orbital dynamics to help the routing, or to either help Dijkstra to converge faster, or to think on alternative routing solutions that might be more efficient. And I'm not going to get into math or orbital dynamics today, but I'm happy to leave you pointers to that. But there are very good mathematical models about the orbital dynamics. And thanks to this mathematical model, one can basically exploit analytical expressions from just basically equations that we can run potentially in a single line of code in order to determine if I'm here in this node, which is roughly the direction I should follow if I want to get the minimal hop count to a given destination. And this is a particular characteristic of the orbital mechanics that governs LEO constellations. And one thing you can do, you can profit from 2 different ways. One, you can feed Dijkstra with that analytical information to help the guidance on the search to the destination node. Or you can even think of alternative heuristics that can also exploit this analytical information to potentially improve Dijkstra in terms of performance. And this is one example of what I'm mentioning today. This is one of the protocols and algorithms we're starting here with the Politecnico di Torino. It's called DiscoRoute. And basically, DiscoRoute exploits these analytical expressions to basically decide whether if I should go left or right from where I am towards the final destination. And one of the evaluations that we're actually getting is that we are able to beat Dijkstra in terms of processing cost. And Dijkstra is optimal, as I mentioned before. The trick here is that we are profiting from specific characteristics of the space network to help Dijkstra to work better or to propose alternative solutions that even work better than Dijkstra. And we can see that, I mean, we can even get better to Dijkstra in orders of magnitude. And reducing the solving time of the routing question is important in systems which are now easily growing to the number of 8,000 or even more number of nodes in space. And also considering that potentially these routing algorithms will run on board. And on board in space, as you know, we don't have air. So therefore, we don't have dissipation. So therefore, we cannot overclock our computers quite a lot. We really need to be super careful about the clocking frequency of our processors up there. So it's not that we cannot run like a data center on a satellite, or the opposite. We typically have very constrained processors. So every processing cycle that we can save is worthwhile to look at. So routing in mega constellation is, even though basically the contribution opportunity is not super high, it's still interesting to look at and observe, especially considering the limitations that we have in onboard processors nowadays. However, this is where we can put our industry hat and say, well, but what we are showing here with Dijkstra and with DiscoRoute, which is this heuristic I mentioned, is that we are assuming that the routing is distributed. So basically, computation happens locally on each of the satellites. And this is not what the industry at the moment is looking at. Why? Because also onboard processors are also challenged by radiation effects and many other things that basically make such a computer vulnerable and potentially generates error results. That if the error comes into a routing decision, then you can easily create like incorrect routes, and you can potentially lose access to the satellite directly. So, and if you do that, you won't be able to even debug the problem here on ground. You will just lose access to such a satellite, and therefore potentially don't even have the chance to debug it. So actually, the state of the art in the industry is to actually move to more centralized routing solution, where you compute the routes on the terrestrial side, you get the commands that you want to your satellites about these routing rules over time, and you configure them. But still, these solutions can also be useful on ground because you can use them to compute them centrally and then use some of the existing paradigms, even like on the technical side, like software-defined networks or P4, which is, again, is one of the solutions that are around to route packets or processing packets on board, which is flexible, but also a bit more challenging in space. But the industry is looking more at a centralized approach now. So also, I think one of the challenges on the routing research in general is also to keep a close look at what actually is feasible for the real systems nowadays in space. So this is briefly about routing. And I guess that most of you, in one way or the other, are interested in AI, like many students nowadays are. Yes, also it's valid the question, what is the role of AI in routing in constellations? We're currently part of this Constella AI project with ESA and together with partners like Thales and GMB. We're actually trying to answer these questions. And we have a series of case studies here. I'm not going to be going in detail, but something that happens in space is that we typically know beforehand quite accurately what's going to happen in terms of orbital dynamics mostly. So we already know how the topology is going to look like in the future. So all the propagation latency is typically something that we can know beforehand, as I mentioned, quite accurately. There is no really need to learn anything on that side. Where we can learn, and there is room for learning, is on traffic-related aspects. So for instance, the queuing latency, the time that a packet spends in a local buffer until that packet is able to go out. And of course, the more intense the traffic is, the larger the queuing latency, and therefore the solution that we compute with Dijkstra, for instance, can be not so accurate. And traffic is an effect that is not so predictable. So here is where maybe learning has a role. And in this project, we have proposed a few use cases where we basically propose different machine learning techniques to understand which is the role, which is the gain that we can expect for applying this type of AI solutions. And one of the main outcome of results is that, for instance, in this plot is one of the example results here. So what we see here in blue is actually, sorry, it's over here. So blue is a Dijkstra that has a God mode access to all the queuing latency on all the satellites. The green one is a Dijkstra which is uninformed with respect to the queuing latency. And the red one is the AI-powered routing solution that trains and learns on these queuing latency patterns based on traffic. And this is on the y-axis, we have basically the average latency that we have end-to-end. So we see that we can get a bit better than God mode, basically, and we get better than the uninformed Dijkstra, and we get close to the God mode. So I think I said it inversely. So blue is the God mode, and green is the uninformed Dijkstra, and we are somewhere in the middle. And we can somehow improve the latency if we are able to train our agents. In this case, we use reinforcement learning, PPO specifically, to get queue tables that somehow try to mark a score on routing decisions based on historical data from the traffic of the system. Still, so far, what we are saying in this project is that the gain that you can get is rather marginal at the moment, at the expense of quite sophisticated data collection system from historical telemetry, plus training on an agent, which happens on ground. This is something interesting as well in this project, because we are with industrials. Like one of the first conditions that was put over the table was, we're going to study AI, but AI and training will always happen on ground. And also inference should happen on ground. So it's not, because we as academic, we typically say, why not running just a distributed AI or a federated system or whatever on satellites? And industrial, this is a moment where it's facing to say, hold on, I mean, if we ever run AI, this is going to run on ground, because I want to inspect the outcome before I send any command to my spacecraft. So this is AI focused on ground. And with that constraint, at least, the claim that we have is that the gains we can get is so far marginal. And potentially, it maybe even doesn't really justify AI at all. At the moment, this can change, but this is kind of a preliminary conclusion that we're getting out of this project. Let me move also a little bit more into another routing aspect, which is relevant. This is still another animation from Mark Handley. And these are the shortest path route that you get between 2 points on the surface in time. And you can see that, of course, these topology systems, these satellite orbits in LEO, and as they move, the shortest path changes, of course, right? There's one opportunity that is better than the other. So you see this yellow line here, like quickly switching between one set of satellite and the other, quite fastly. And in principle, this is no issue. I mean, as you said, as we know beforehand, we can run Dijkstra or Disco route or similar logics and just run them periodically to check which is the best route at this moment, and we can quickly switch to the most performant route. It seems to be no problem in principle with that. But join me in trying to understand this plot very quickly. So this is the time on the x-axis, and here on the y-axis, we have the end-to-end delay from this source and destination pair. As time goes by, we have different best routes at that moment. And these little U-shapes that you see are essentially the route that is the best at during that moment. And this U-shape is because basically there is a satellite that is on the horizon, is moving away, and the latency of the route also changes in time. But still during this period over here, that is the best route that we can get. And what we see here is Dijkstra in yellow. So you see Dijkstra, the little pieces of Dijkstra is mostly down here, because Dijkstra is, of course, offering us the optimal end-to-end latency, but it's quite hysterical in the way it changes. It really changes super fast, because maybe just a little change in route will trigger us, no, we should move to the fastest one. And this is why we get a lot of yellow underneath, but there are also very little pieces of yellow. The other extreme would be using a kind of a classical set cover algorithm, where I want to cover the routes in during all the duration by minimizing the number of routes we use. So in other words, I'm maximizing the validity time of the routes. And that is where we get the green plot on the top. Here, the graph is there is a shortcut here, right? So we are talking about 155 milliseconds end-to-end delay versus 88 with Dijkstra. Why would we care about this? For one simple reason. On top of the routing path that we select, we are running a congestion control algorithm like TCP. And TCP is a congestion control algorithm that keeps tracks of the bandwidth delay product, or the capacity that that path actually has. And if we change that capacity suddenly out of one moment to the other, TCP gets crazy. Because TCP was designed to work on relatively stable routes. And we're changing the routes every 10 or 20 seconds with Dijkstra here. And we have studied this effect, actually. And definitely the route changes has a huge impact on the performance on TCP running on top of that. Maybe the core focus here is this plot I have on the right here. So here are Dijkstra, set cover, which maximizes the duration, and some intermediate techniques. And in particular, Tenacious is one heuristic that we found quite well performing. And here we have the end-to-end delay. And here we have the data rate of a TCP Reno running on top of that system. Reno is one of the congestion control algorithms that is used in TCP. And if you see, we can see that the Dijkstra, which is the most historical changing one, is here. So it's actually is the best delay that we can get, as you have seen on the previous plot, but also one of the worst throughput in data rate. Why? Because of these changes, the round trip time of the timeout of TCP gets inaccurate, and you get basically a lot of backoff and congestion window reduction a lot. And also you get a very interesting effect, which is overtaking. When you move from a slow route, which is high latency route, you have a new route that is much better in latency. It happens very often that the new packets sent over the new routes will win with respect to the other and will get to the destination first. And this in TCP is read as kind of is like an out of the order arrival. And TCP interprets that all these packets that are still en route were lost on the way, because you receive a stream of new packets on the destination through the fastest route. And this triggers a congestion window reduction and a reduction of throughput. And this is why we see Dijkstra performing so badly. The interesting thing is that we go to, okay, let's maximize the validity time of the route so everything is super stable. That's not also so intuitive because the cover is here. So we are getting the worst latency, but we are still not getting a perfect throughput, at least compared with some of the other heuristics we try. So also because high latency also makes TCP behaves badly, right? Because TCP confuses latency with congestion, right? So the natural, I mean, the key point I want to highlight you from here, that even on transport layer, there is a sweet spot somewhere in congestion control that needs to be designed and thought in correlation with the routing computation as well. And this is one of the topics we're actually is actually motivating our research quite a lot. So we're moving towards NTN nowadays. So also, I want to briefly touch on direct-to-device communications because it's also quite a hot topic, and I think it's worthwhile also putting this on the table. So we are seeing all these mega constellations thrive, and we have the cellular and the mobile communications community trying to catch up. And non-terrestrial network is kind of the key word for upcoming 6G. And 3GPP is pushing forward this intensively because my understanding is that with 5G on our phones, what else do we need? We can see a movie or we can see whatever we want. Well, what they are offering is coverage even on underserved areas. And NTN, non-terrestrial network, is the keyword, and direct-to-device seems to be even a more stronger keyword here also to look at. And direct-to-device or direct-to-smartphone, when we're talking specifically about smartphone, has also catch a lot of attention recently, mostly from the industrial side. And there is a series of generations here about how this direct-to-smartphone can be thought of. I just want to focus on the last one, which is we are trying to get unmodified cellular chipsets, like the same 3GPP compatible chipset that we have in our smartphone, to connect directly to a satellite, like without modifying anything on the smartphone. Even though we have some previous steps here, like taken by Apple, you might know that some iPhones had a Globalstar connection, you can get SMS and some support. But now we're starting to talk by Starlink mostly and a few other companies about direct to satellite communication from our own modified device, achieving this performance that Starlink actually showed feasible only a few months ago. If you haven't seen the news, they are actually showing up to 17 megabits per second of downlink capacity using direct to their second generation satellites, which actually all these are the antenna arrays on these satellites that can directly connect to your satellite, which quite a reasonable performance. A few megabits per second is actually something quite interesting to see. And the risk, of course, shaking the market with basically a little waiver here or a little comment is that they were basically using the full satellite beam with a single smartphone to get these metrics. So eventually, this will need to be multiplexed across as many devices that you have on the coverage of the satellite. And this is where scalability becomes an issue, right? Because you have a satellite with potentially quite a big footprint over the surface, and this will need to be shared about multiple users. So this will divide itself quite a lot, but still SpaceX is making good partnerships with different operators around the world to provide such a service. And it's a perfect use case for what they are trying to do, which is making a good use of spaceships, which is deploying thousands of more satellites so that you can basically cope with these scalability requirements of direct to the satellite, direct to smartphone communications. Starlink is not alone here, so just quick, I will leave you to explore this slide as well offline on your side. But Starlink is, as I mentioned, is kind of main push here. But we have AST and Link Global. These are two smaller companies that are trying to get the same. Just take a look at the picture here. The trick part is to close the link budget from 600 or 700 kilometers distance to a device which is designed to close a link budget with a base station a few kilometers away at the most. And the tricky part here is that you need your satellite to compensate the loss of the channel, basically with the satellite antenna. So we have a few competitors here with Starlink that are basically deploying this huge satellite to make this possible. There is one, I think, worthwhile attempt, on my opinion, on Iridium, which is one of very old actor in space communications, which is saying, let's wait for a second, let's try to standardize this, let's agree on what the interfaces are going to be. And they're trying to take a kind of a role of integrating everyone and try to agree on what they're going to do. The reason is that satellite operators like Starlink or Link or AST, they don't own the mobile spectrum that you need to communicate with this cell phone. The owners are the operators on the regional level, on a country or a national level. So it's highly likely that satellite operators will need to make deals and cooperate with mobile operators locally for this to thrive. And there is a big push there because, of course, satellite operators will want to get global spectrum so that they can provide the service on their own, like trying to make a place on the mobile operation, on the mobile networking side, also on the terrestrial side. And the terrestrial mobile operator will also want to compete with this and provide end-to-end solution as basically they are 3GPP service providers. But there is no sense for a terrestrial operator to build a constellation for their own. It's also impossible. It makes no sense because LEO satellites cover the full planet, and your country may be just a little percentage of such a coverage. So there is no sense to deploy an infrastructure in space as a terrestrial cellular operator. So also, I think there is a back and forth here about what's going to happen here. And this also has an open question on the mobile communication system, how these protocols and how this system will actually eventually integrate and work all together. I'm going to spend a few words, but we will move forward, which I think satellite IoT is one alternative way of thinking this. So instead of communicating with on a broadband scale to get like video calls and so on, there are a few space systems like Kinéis, which is the video I'm showing here, that are trying to obtain low data rate, low data volume, high latency solutions using the similar direct-to-device type of communication. But here, the pressure on the infrastructure side is far lower because we don't really need to have a video call via satellite. We just need to send a few bytes here and there to collect humidity from a sensor somewhere. So satellite IoT is quite appealing to rethink the story with potentially CubeSat, far smaller satellites, and also including the utilization of standardized protocols that are already operative in low power wide area networks, which are long-range frequency hopping express spectrum or LoRa kind of accumulations, and also 3GPP NB-IoT as well as part of these direct-to-satellite IoT systems, which seems to be an alternative way of thinking about networking in space, which is potentially more sustainable at least. You don't need thousands of satellites, you just need to collect a few bytes. So this might make a few more sense. There are a bunch of smaller companies that are moving forward with this. Because it is smaller in infrastructure, smaller companies can participate. But still nowadays, because of the increasing growing of Starlink, these small startup companies are a bit, let's say, cautious here about whether if Starlink will basically also dominate over the IoT domain. So far, this has not been heard of, but it wouldn't be surprising that from one moment to the other, also Starlink start providing services that basically remove this company from the competition. Let me skip. There are a few research topics about IoT, which I'm very happy to spend a word afterwards. But as I said before, going back to the routing topic, when we think about sporadic communication with space in IoT, also the routing becomes a bit more challenging. And I'm starting to give the room for Jorge's topics afterwards. And try to follow me on this example over here. When we have these sporadic communications from few satellites that orbit the planet, and eventually you get to connect to some isolated region, like this one in blue here, that is not connected to the internet in red, your satellite can act kind of a data mule. So when you pass by over such a node, you can collect the data, and you can carry it with you until you get to a ground station or something that you can offload the data to the internet so you can get it to your server, for instance. And on the way back, the inverse path is also valid. So the server has a reply for the data, and that server can actually ask the question, so which is the ground station I should use if I want to get to my destination node the quickest possible? And maybe in this example, for instance, it might be the case that maybe this other ground station is the way back, because maybe a satellite is going to pass by here, carry on my data, and deliver that to the final destination again. And as you can see, this communication paradigm is a bit more what I mentioned at the beginning of the talk, which is store, carry, and forward. There is no end-to-end communication on a persistent way, but data is flowing on a step-by-step way to a destination, therefore achieving data transport on a high latency scale. I mean, this is not immediate. You cannot make a voice call on this, but you can still transport data, even potentially with just one satellite even, right? So you can have far more sustainable constellation system that are able to transport high latency data. And this is a concept which is popularly known as the Green Road Network. And the lateral networking is the core technology that can enable these networks to operate. And if I talk about high latency, I will move slowly to my third domain that I want to share, which is deep space. When we move to the moon and beyond, then the latency is not product of little satellites in the constellation, as in the IoT case I presented, but it's a consequence of the propagation latency at the speed of light at very high distances. And for instance, in Europe, we're highly motivated by the Moonlight project, which is also in accordance with NASA LunaNet project, where there is a serious intention of deploying assets in the moon shortly. And the moon is definitely one of these cases where we start to get sporadic communication on one way because the Earth rotates. So you have sporadic communications with lunar assets, but also very high latency because of the distance of 1 second propagation time to the moon, more or less. The same applies if we go and look farther into Mars and other planets. So the key question here is, how do we model the network to reason about routing in such a context? And one of the key concepts here is contacts. We are not longer talking about links or stable links like in classical network systems, but now we should talk about contacts because those links are actually has to exist only during a time interval. So a contact is a better way of expressing this. And during a given contact, I can already understand that there is a volume of data that I can convey during such a time frame. And also, the contact can easily incorporate the one-way light time latency of the contact to basically consider the propagation time there. So instead of our edges in our graph are no longer stable, but are contacts that exist and stop existing after a given time frame. And this is a far more interesting model to reason about this type of routing, these type of systems. Also, another comment is that in space communications, typically forward and return channels are not symmetric. So we typically want to download more data than the data that we want to upload to the satellite or to the spacecraft. Why? Because we typically want to command the spacecraft, eventually do some firmware upgrade, but on the downlink, I'm getting all the data that I'm collecting from the spacecraft. So it's highly common that we have very different throughput ratios between uplink and downlink. So contacts are also a very interesting way of actually modeling such a bidirectionality, these unidirectional communications aspects. There is a second quick aspect that we'll just try to cover very quickly, which is also the start time and the end time of a bidirectional contact is not the same over long distances. Why? Because by the time that my satellite is emerging on the horizon of the remote planet, I will have already had such a latency time to start transmitting before, so that my data arrives at the moment where the satellite is emerging on the horizon. So more kind of a baseball ball that you throw in advance, so that the satellite, when it's appearing on the horizon, it will get the signal that you're sending. And the same happens when the satellite hides in the horizon. And if you think about it, the start and end time of the transmitting time of that satellite and that ground station are actually decoupled in time. So this is when you need contact to separate transmission and reception, because high latency actually breaks this bidirectional principle that we're so used to see on the internet. And the question is, how do we build graph with contacts? Because we don't have a stable graph anymore, we cannot write Dijkstra anymore. The idea is to profit from contact plans, like what we have up here. We have a list of contacts, and based on that contact, we can build quite an unintuitive data structure that will briefly present, we can discuss if needed, where the reasoning is as follows. The nodes or the vertices of the graph are no longer the network nodes themselves, but the contacts of the contact plan. So I'm actually connecting contacts in the graph. And this means that if I have a contact between A and C, then I can connect that contact with contacts that emerge from C, which is the destination of this contact in the future of this contact here. So based on this very simple principle, I can construct contact graph like this one that represents the time evolving network topology, but in a static data structure. And the fact that it is a static data structure means that we can run classical graph algorithms on top of this without bothering too much. And this is what contact graph routing actually does. It's one of the most popular algorithms for routing in the store carrying forward networks. It basically uses this time evolving network model that is expressed in a static data structure. So we can come back later to this if you are interested, or you can reach me for discussing this. The challenge that we have on routing over contact graph are threefold: scalability. I mean, contact graph can get quite big, and also, as I mentioned before, onboard computers are constrained, and this is the result that we got from implementing SYNCGR in an onboard computer from one of the CubeSat, and the computation time can get to 100 seconds on contact plans in the order of more than 10K contacts. So this means that you cannot have an onboard computer thinking for 10 seconds, which is the best route to get to a destination. Scalability is definitely one of the key concerns here. Congestions in ETN in general is a routing-related aspect, super difficult to tackle, because you don't have immediate feedback from the other node, either because there is high latency or either because there is a retention period on the way. You don't have feedback from the other node, and therefore you don't know whether that buffer from the other node is going to be full or overloaded with the data you're sending. Finally, uncertainties. Contact plans are not always perfectly predictable. You don't know, fails can happen and so on. So on top of the complexity, we are adding uncertainties, and a stochastic model actually forces us to rethink as well about scalability and so on. So quite a challenging problem. And finally, to close my talk, there is a final challenge, which is how do we integrate all these routing solutions that we have so far? We have routing for store carrying forward networks, which are perfectly scheduled, like CGR. They exploit a very static data structure. But also we have uncertainties in space, which is a challenge I mentioned. We have interference, we have weather-prone effects in optical links, or even we have nodes with very little processing capacity. So how do we think on routing on a solar system scale with this type of system? How do we integrate different routing solutions? And also not to mention cases where we don't even have any information of what the topology looks like. So this is also another open challenges that we have in the solar system internet scale. And with this, I basically got to the key points I wanted to share with you. I am, only a few minutes over, so I think we're on track. On the mega constellation side, the wrap up here is that, so classical algorithms are still preferred over AI. I think this is one of the key points I can take from what I presented today. the model and the impact of TCP over routing in mega constellation is still not understood fully, in my opinion, yet, at least from what I see in the literature. The direct-to-device is opening quite a lot of concerns about how we are going to connect our mobile operators on ground and future satellite system. I think that satellite is attractive. It is unclear which of the standard LP1, these low-power wide area networks techniques will prevail, and whether, yes, I think it's motivating to have this resource-efficient paradigm on the table to rethink about these mega constellations. Do we really need all these huge mega constellations with all the challenges it brings that I'm not mentioning here, like space debris, sustainability, pollution, etc. Maybe satellite IoT gives an alternative way of thinking this. And yes, and finally, the solar system internet, where we start to look into far-looking planets or assets. Which is the right protocol architecture for the SSI. Jorge will give us a bit more about insight there. It's still under debate. So including time aspect in network protocols like routing is difficult. I mean, this is the challenging part. Yes, you pay with scalability, you pay with a lot of complexity and so on. So really bringing time, which is in essence, I think this is what's happening here. When you move from the classical internet protocols into deep space protocols, the challenging dimension that you're adding is time. Because in terrestrial internet, time is not a variable almost anywhere. But in DTN and deep space, it is kind of the main dimension that you want to look at. And yes, the challenges I mentioned. So, I mean, the core messages, I think also Jorge will try to also insist on this claim over here, is that space makes us rethink quite a lot about the basic assumptions on how do we design protocols and algorithms for classical networks, for traditional networks, which are non-space related. And I think this is, on the one side, it's fun because it's really challenging. It really makes you go down, for example, with this to TCP. Why TCP behaves like that? Because the assumption of end-to-end connectivity allowed the designers to provide Reno or the congestion algorithm we know nowadays to work efficiently on the internet. But when you start to, let's say, challenge some of these assumptions, then things are not working so much as expected. And that is, in my opinion, where research opportunity is present, because you can find a way to either fine-tune what is existing or to even completely think on new solutions for a space domain. And this is kind of the core message I wanted to leave you with today. So that's basically it about me. I'm happy to move to part 2, unless, I mean, we can take a break, we can take questions. I think we're open to accommodate the mood as you need, guys. I don't know, Robert. Yeah, thanks.
Can you go back to the slide showing the end-to-end delays?
From the
one of the first slides.
Yes, let me take. I think I know which one you're referring to. Okay. This one?
Yes.
Yeah.
Not the end-to-end delay, you satellites, but from 2 ground stations, right?
Correct. From 2 ground points. Yes. Potentially 1 terminal and 1 ground station. Yes.
Because these packets perfectly reflect the visibility pattern between a ground user and the satellite.
Yes.
So I was wondering, so the inter-satellites part of the space segment is not affecting so much the overall shape of
the shape. No, the major effect affecting the shape is the ground to satellite part, and then the satellite to satellite also has a U shape, but it's less intense like the one we're seeing here.
Because as the time goes, I would expect also the space segment to change.
Yes, of course, it does.
Like,
Sorry?
Looks like it's not changing.
Yes. Here it looks like it's not changing. Where?
Since these patterns perfectly reflect the visibility pattern between a ground users and satellite, it looks like the overall end-to-end delay between different stations is mainly depending from the ground to satellite method.
Yes, it is. I mean, the shape is depending, as you said, on the ground to satellite, but the position of this curve on this axis is more about the number of hops that you have on the way, right? And the distance that you need to traverse to get to the destination. Yeah. I can share with you the paper with this. Yeah, we do have also a differentiation about what's the contribution of the space to ground or the space to space only links here. I think also the reference is here if you want to look at it. Sure.
Questions? I just would like to ask about the direct to smartphone, direct to device communication. How's the architecture? Is it thought like for the downlink only, just like VSAT, or also for the uplink?
No, it's both bidirectional, uplink and downlink. So this is
the gateway is out.
Yes. So yeah. So this, as I said before, this experiment here, they showed. I don't have the. I mean, the data rates are the one I showed in the previous slide. So it is 18 megabits per second downlink and 7 megabits per second uplink. This is what Starlink reported, right? So I guess we should believe them.
About the power of that.
I mean, the smartphone is unmodified smartphone, just unmodified smartphone. The modified part is on the satellite. So 2 comments there. As I said before, if link budget wise, everything is on the gain of the antenna on the satellite, most of it. Potentially some sensitivity improvement and so on. But if you see kind of these pictures, this is a 64 square, this is an apartment in an antenna. So the way you can close the link budget is by an antenna. And then there's also a second aspect, which is more the MAC layer, which is the time advance and the Doppler correction aspects, which in 3GPP, they are designed, in 4G, they are designed to operate in a terrestrial environment, like when you're on a train or in a car. But when you have a 7 kilometer per second satellite, the frequency compensation and the time compensation, they need to hack the satellites to cheat your smartphone so that it believes that it is connected to a ground station here on ground. One of the things that I'm not an expert on MAC layer in 3GPP, but what I heard is that you can do that for one smartphone easily, but if you want to hack those values for all smartphones, for multiple smartphones, you cannot do that. And this is where one of the arguments of why Starlink actually demonstrated this with only one smartphone only, also with a MAC layer limitation. In 3GPP, the NTN releases are actually dealing with this problem also, so that you can accommodate frequency compensation and time compensation also for the satellite case. So they should be solved in 6G onwards as well. Yeah.
A curiosity, regarding the mega constellation, how much do we know about, for example, Starlink routing the internals?
Zero. I mean, this is one of the main, as a researcher, one of the main challenges here is that everything at the moment is on the industrial side, and everything is closed and everything is proprietary. So everything we have are speculations and some reverse engineering efforts of some universities that are trying to hack and inverse what they are thinking in terms of routing, but really, really minimum. Which is, I mean, this is one of the main negative things at the moment, because we don't really know how to help the industry with this, right? Because we don't have a sense of what they are thinking. I'm getting some insight from ESA and some industrials there, but regarding Starlink, we know little to nothing of what they're doing. Okay. Yeah, sorry. Yes.
That's about the direct to smartphone.
Yeah.
Maybe it's a master.
Do you have a slide in mind?
Okay.
This one? Yeah.
The ST Smart Mobile, the antenna is about 46.6. But for Starlink, it's only 25 meters.
Yes, Starlink is smaller.
Yeah, but I know that ST use maybe K or KU bands, so the frequency is high. But for the Starlink, I know it's have a cooperative with T-Mobile.
Yes.
So they use the LTE frequency sometimes, the
Correct.
3 band or 3 band. So you use the low frequency, maybe the high wavelengths. So and they has a small antenna. So I think at the beginning of the satellite antenna is really low.
Yes,
So
it's
how to-
lower.
So how to get to the
Again, we don't have the technical specification of the antenna or anything here. This is only speculation. What I read from the community is that Starlink was able to make a demonstration with the smaller antenna, but on very high elevation passes. So if the thing is that if your device is here, your satellite appear on the horizon, in such a very challenging condition, you can have it to 2,500 kilometers of distance. And when your satellite is on the top, you're in the closest distance, you might be 500 kilometers or even less, 400 even.
Yeah.
So what Link is promising that they can do with this satellite, they can establish the connection already here in the horizon at the very long distance. This is where antenna plays a role. But Starlink, what we understand is that they basically operate where you have from the 80 degrees to 90 to minus 80 to, let's say, to 100 degrees, only on that region. So that is where a smaller antenna can establish a link still with you, but over very limited cone of coverage. And this is one of the arguments that why also I think this is a good use case for Starlink, because if you have such a reduced cone of coverage, then your satellite will be already gone, even if it's still right on top of you, but you will need another one coming next. And this actually argues why.
I think maybe one satellite cannot do that thing. Maybe they need to cooperate with different satellite for Starlink.
Yes.
2 or 3 or maybe
Yes. Or maybe multiple satellites on the same cone, definitely. Yes. Sure. Yes.
Demonstration what is done with the beat on the satellite or on ground.
Sorry, I didn't go to this first part.
The demonstration that you show us is done with the satellite
Good.
ground or on the satellite.
So let me profit from that question to explain something briefly I didn't explain. So in 3GPP, we typically have either transparent or generative payloads. The transparent payload is a way of operation where the satellite basically just beams down the digital sampling of the signal to the ground, and all the E not B logic is on the ground. And the regenerative payload is where the E not B is on the satellite, so the decoding happens on the satellite, and the MAC layer is mandated from the satellite. The answer about Starlink, we don't know. What they say is that the future generations we have regenerative payloads, so the E not B fully operative on the satellite.
But also regenerative payloads that would be also in routing towards
Right.
satellite links.
Exactly. For the regenerative
Each
payload,
satellite would have to decode and
yes, each satellite needs to decode. I mean, but it's the only way. If you really want to get the latency constraint from 3GPP, you need to have the E not B on the satellite. I mean, because doing all this beaming down to Earth, decoding here, sending the response on the digital sampling uplink, you don't meet the latency constraints. Yeah. Good. Thank you, guys.
It's worthwhile to mention that we have an ongoing collaboration with Professor Juan Freire, started in 2019, I guess, together with Professor Dovis. This collaboration